Hello. So we're going to continue on and talk about scatterplots. Um, this is where we're kind of just exploring the relationship between two numerical variables, and we're going to also talk about something called a correlation coefficient. So scatterplots look something like this. Again, it's the a graph for showing two numerical variables. So this example is data I collected from students that asked them how old was their mother and how old was their father when they were born. So these are mother's ages versus father's ages. So each point represents a student. And you can see how old their mother was and about how old their father was at the time that they were born. So when we are looking at scatterplots, if you were asked to describe a scatterplot, there are three important things that we want to make sure and include. Um, the first would be the strength. The second would be the direction, and the third would be the form. So when we say strength, we're kind of determining or looking at how kind of close the points are to each other. Do we see a specific pattern, or are the points so spread apart that we can't even really truly see a pattern? So if we can really strongly see the pattern because the points are all fairly close to each other, then we would call that strong. If we can see a pattern, but it's a little bit more spread out and it's not as concrete, we might call it moderate. If it's to the point where we can almost not even see the pattern, we would call it weak. Direction is positive or negative, so that typically means, as X goes up, what is Y doing? So typically we're going to say, like I said, positive or negative. There might be some situations in which the points kind of go up and then come back down, and we would want to mention that. It's positive from this to this, and then it turns negative. But we generally want to know what's happening to Y as X increases. And then for form, we're looking at, is it linear, meaning do the points generally form kind of a constant increase or decrease, or do we see some type of curve, or maybe even a exponential situation happening where it's not really linear? For now, we're just going to say linear versus nonlinear. You don't have to say exponential, you don't have to say quadratic. You can just say, hey, this doesn't look linear. So for this one, when I describe this, and the fourth thing, I didn't mention this on the list, but this is always with AP statistics, is context. So that means when I describe this association between these two variables, I need to mention the actual variables by name. So what I would say for this one is that I see a moderate, positive, linear, you could say fairly linear if you wanted to, association between mother's age and father's age at the time of student's birth. So moderate because I can see the pattern, but it's not super close together. Definitely positive as mother's ages increase, so do father's ages. And I would say fairly linear. I don't see any sort of curve or even exponential situation happening. So I would call that fairly linear. So what I want to look at now is kind of thinking backwards. I'm going to give you two variables, and we're going to think about what we expect the association to be. So I'm going to give you a minute to think about it and choose what you think would be the relationship between gas prices at a gas station versus the number of visitors to that gas station. So when I think about these types of questions, I tend to kind of draw, even if it's just in my mind, a little graph, and I'm going to say this is the prices, and then we'll say this is the visitors. And then when I think about this, might want to think about, okay, if the gas prices are really low, comparatively, would we expect a low number of visitors, a medium number of visitors, a high number of visitors? And probably if gas prices are super, super low, especially compared to the gas stations around it, I'm expecting there to be a lot of visitors, right? Maybe it's a weird day and it's raining, so maybe not as many. But generally speaking, probably a higher number of visitors. Okay, same thing if the gas prices are really, really high, I don't expect to see as many visitors. So maybe it depends day to day. Maybe it's the only gas station that's nearby. So it might depend, but generally speaking, we probably see on most days a lower number. And then in between, there's medium price of gas. We expect to probably see a moderate amount of visitors. So what we can kind of see this picture, if I were to guess, I would say that there's probably a negative, probably moderate, because it's not going to be perfect, maybe even strong. Moderate to strong, and I would guess fairly linear association between gas prices and number of visitors to the gas station. Right? It's hard to know exactly perfectly what would happen, but this is a kind of good guess based on what we know. So let's look at The next one, which is what type of association do we expect to see between number of daily umbrella sales and number of car accidents that day? So I'm going to give you a second to think. What do you think the relationship would look like? And then we will talk about it. So again, I have my little graph. I have number of umbrella sales on the x-axis. I have number of car accidents on the y-axis. So I'm going to think about, okay, if there are, I'm going to start high this time. What if there's a really high number of umbrella sales one day? It's a really high number of umbrella sales. Well, if I think about it, there's a lot of umbrellas being sold that day. It's probably raining outside. And if it's raining outside, we tend to see more car accidents than on a day where it's not raining outside. So if there's a lot of umbrella sales one day, I might not be surprised to see that there's more car accidents. Now, this is definitely not going to be perfect because it's not completely strongly super related. So maybe I might see a little bit more spread outness of these numbers. Same thing if there's a low number of umbrella sales that day, it's probably not raining. And when it's not raining, we tend to see fewer accidents. So again, it's not going to be perfect. So this is something that even though these variables don't seem like they would be related, I'm probably still going to see a somewhat positive relationship. Now, will it be strong? Probably not. I'd probably say moderate, maybe even moderate to weak, but I do expect to see some type of pattern there because even though number of umbrella sales don't cause car accidents, there's still kind of a relationship happening. It's just not a causation relationship. So that's something that's really important to keep in mind when we are dealing with variables, when we're talking about relationships between variables. We're not necessarily saying there's a cause relationship or a cause and effect relationship. We're really just talking about, do we see a association? As one variable changes, does the other variable change in a specific way? I always like to look at this website. I'll put the link in the thing. It just kind of shows really random relationships between specific variables, and it can be really interesting to see all the weird relationships. But a big thing to keep in mind is that just because we see an association or relationship between two variables does not mean that one variable is causing the change in the other. There could be other things happening. So, is there an association? I'm going to look at a new set of data now. So, we're looking at, for SAT, this is in 2000 to 2001. This is really old data. But McNeil students' scores on the math section versus their score on the verbal or reading section, whatever you want to call it. So, if I were to look at this relationship, I'm going to give you a second. What kind of relationship do you think there is between these two variables? Is it strong or weak? Is it positive or negative? Is it linear or curved as in nonlinear? Chances are, most people, when they see that, say maybe moderate to strong, positive, fairly linear. What about this one? Again, I'm going to give you a second to think about it. Is it moderate, strong, weak? Is it positive or negative? Is it linear or nonlinear? Now, typically on this one, people will say that it's weak, that it's maybe a little curved. You kind of see a little bit of a curve there, and that it's still positive. So if you didn't notice, as some of you probably did, those are the same graph. So even though they look different, that is the same exact information. It's just on one of the graphs, we are a little bit zoomed in, so we're seeing a little bit more separation between the points. Here's another example of that, right? We have our original mother's age versus father's age graph. If I zoom in a little bit and exclude some of the data, it looks a lot different. So this one I might call moderate positive. This one I might say weak, maybe even no association, because it doesn't seem to have any kind of pattern. So that makes a big difference. Where we look at our range, how zoomed in we are on the data or zoomed out, if we're restricting part of our data, is obviously going to make a huge difference on what our visual guess of the relationship is. So our eyes are not always good judges of the strength of a linear association. So we do need some kind of numerical measurement that gives us a stronger idea of what's going on. And we call that numerical measurement the correlation coefficient. We use the letter R to represent that number. I don't know why they chose R. That's what they chose. So correlation coefficient basically tells us it's a measure of the strength and the direction of a linear relationship. So one thing is correlation is always a number between -1 and 1. The closer it is to -1 or 1, the stronger the relationship. The closer it is to 0, the weaker the relationship. So this is one up here that has an R value of -0.95, so pretty close to -1. Notice that the relationship we see is pretty strong and negative. So the negative positive part is telling us about the direction, and then the number itself, how close it is to 1 or 0, is the strength. So this one is one we would call strong and positive. So its R is 0.95. Here are some what we call moderate. So R is -0.6 and R is 0.6. So negative just means it's a negative direction, but it's about the same strength. This is one we might say has an R value of close to 0 because it doesn't seem to be positive or negative. There doesn't seem to be any kind of pattern or trend there. Okay. Typically speaking, in terms of the actual number, this is what most statisticians agree on. Between 0.8 and 1, we would call strong. Between 0.5 and 0.8, we typically call moderate. And less than 0.5 is weak. Notice that's absolute value of R, because remember, R can be negative. That's the direction part. But the actual value of the number itself, the absolute value of it, is telling us the strength. So how is R calculated? Well, it involves z-scores, and there's a pretty long process to it. Here's our z-scores for each mother's age, father's age data. So I just converted all of those numbers into z-scores, and I now have them. The red lines are the x and y axis, and these are all of the z-scores. Once we find all of the z-scores for each of the values, we use this lovely formula to calculate R. So 1 over n minus 1 times the summation of the z for x times the z for y. So for every point, we do z times zx times zy. We add all those values together for all of the points, and then we divide by n minus 1. That is never something that we're going to do by hand because it's very tedious. Our calculator does it perfectly well. We'll talk about in class next time how we do it with our calculator. But it is good to know where R comes from. It is calculated from z-scores, and if you remember from the last unit, z-scores in terms of units don't really change z-scores. Z-scores are standardized scores. That's the point of them, is that they're always kind of on the same scale, which is important for R. If we're going to have it work for all different kinds of data with all different kinds of scales of variables or numbers, we want it to be standardized. So we use R. So important facts about correlation that you need to know: it does not depend on units. So scaling, shifting, changing units will not affect correlation because it's calculated from z-scores. So this is an example. It's showing the height versus the weight of a bunch of different people, heights in inches, weights in pounds. If I convert that, heights in centimeters, weights in kilograms, we see pretty much the same exact data. So it's going to have the same correlation. Another fact is that correlation treats x and y symmetrically. So if we were to swap the x and the y, this does not change correlation. If you remember the formula for correlation for R, we're multiplying zx times zy. So multiplying either way doesn't change the value of the number. So here is the mother's age, father's age. The correlation for that data is 0.75. If I were to swap the x-axis and the y-axis and put father's age on x and mother's age on y, notice the scatter plot doesn't look exactly the same. The points are in slightly different places, but the correlation, the relationship between those two variables isn't changing. So the correlation is exactly the same. We would still call it moderate, positive, etc. A couple other things to note. It's measuring the strength of a linear association between two numerical variables. So the word correlation should only be used for talking about numerical variables, two numerical variables, and specifically it's measuring how strong the linear association is. So when we look at data, we need to be careful of that. I'll show you an example in a minute. Other thing to note is that correlation is unitless. It does not have a unit. It's not like R equals 0.95 seconds. It doesn't have a unit. It's just a number. And it can also be very sensitive to outliers, which is something we're going to explore more in a future lesson, but I'll show you a little bit of that today. How sensitive it is just kind of depends on how strong the correlation was to begin with, how many points there are in your set of data, where are the outliers, etc. So, as I mentioned, correlation measures the strength of a linear relationship only. So this is a graph showing the baking temperature for different baked goods versus the score they got. Like maybe they were scored on a scale of 1 to 10 in terms of how good they tasted. So as you can see, we have a pretty obvious pattern. As baking temperature goes up, score goes up to a certain point, right? And then as baking temperature continues to go up, the score goes down. So we have kind of a sweet spot. If it's baked too long and too high of a temperature, it's going to be burnt. So we have a very clear relationship, but that relationship is not linear. So if I were to calculate R for this set of data or correlation is probably going to be pretty close to 0. So if I were just told the R value for this without seeing the graph, I might think, oh wow, there's no relationship between baking temperature and score. There is a relationship, it's just not linear. So just keep that in mind. We can calculate correlation for any set of numerical variables, but it's only going to be useful to us if it's linear data. And so it's really, really important to look at the graph of a set of data before deciding how strong or weak that relationship is. R is only telling us about the linear relationship. So it's going to be a misleading value if the relationship is not linear. So I'm going to look a little bit more at outliers. As I mentioned, outliers can affect correlation pretty strongly. So this is a mother's age versus father's age graph. This is a different set of data, so R is a little different, but 0.8. If I were to add one data point right here, someone who the mother was 20 and the father was 50, right? We have one data point. My correlation is now 0.67. So we went from something that was technically strong and positive, and just with 1 point, we are now in the moderate section. Another more extreme example, this is looking at number of shoes that someone has, number of pairs of shoes that someone has versus the amount of sleep they got last night. So clearly not something we expect there to be a relationship between. And we see that. The R is negative 0.067, so pretty close to 0, pretty much no linear relationship. But if I add one single point, someone who has 80 pairs of shoes and got 24 hours of sleep last night, we now see that R is 0.4. So it changed from pretty much 0 to 0.4 just from one single point. So things to keep in mind. Outliers do have a pretty strong effect or can have a strong effect on correlation. So we're going to look at a couple of sentences based on what we've learned about correlation and what it represents, and we'll see if you know the rules. So first sentence, there is a strong correlation between gender of American workers and their income. So is it true or not? If it's not true, think about what's wrong with it. That is not a correct sentence because gender is a categorical variable. So correlation is a word that is only describing this relationship between numerical variables. It can only be calculated for numerical variables. Second sentence, we found a strong correlation, R equals 1.09, between students' ratings of faculty teaching and ratings made by other faculty members. That one is also not correct. Even though there could be a strong correlation between those two variables, R is a value that should never be bigger than 1. 1 means it's a perfect straight line with an exact slope that never changes. So beyond that makes no sense. Somebody did their calculations wrong. So this is incorrect. Third sentence, the correlation between planting rate and yield of corn was found to be R equals 0.23 bushels. Also not correct because R is not something that has a unit. So even though that could be the value of the relationship between those two variables, it should not have a unit with it. So it would just be R equals 0.23. All right, last one. We are looking at the relationship between gender and type of TV show they like to watch, people like to watch. So it's collecting data on those two different regions. So region A, region B. So if I were to ask you, there is a stronger correlation, or if I were to say there's a stronger correlation between gender and preferred TV program in region B than in region A, is that a true statement or not? And the answer is no, because the word correlation is specifically for numerical variables. So I could say that there is an association between those two variables, between gender and preferred TV program in region B, because I do see that in region B, females have a stronger preference for dancing, males have a stronger preference for football compared to region A, where it's mostly equal. But I cannot say the word correlation. It's kind of a trick question. So be careful. Using the word correlation is for numerical variables only, and it's only describing how strong the linear relationship is. All right, that is it for today. See y'all next time.